All right. Welcome, everyone. Thank you for joining us today. This is our bi-weekly Viceroy CySERS virtual seminar. We actually had a seminar just last week, so this is an off-season, and so we will get 2 weeks from now, and we'll get back to our bi-weekly sessions from now on. But today I have the great pleasure of having Dr. Mohammed Ismail being our speaker, who would be talking on emerging technologies for cyber-physical power system security. And I don't want to spoil it, but the emerging technologies are very important for the conversations we are generally having. He would talk about AI and quantum in particular in the context of power system security. Dr. Mohammed Ismail, he is the director of the Cybersecurity Education, Research and Outreach Center, also called CEROC, and an associate professor there of computer science at Tennessee Tech Technology. And he leads a very active and large group doing a lot of activities around power system security and has extensively published in this area. And as a leader of CEROC, he is very much engaged with outreach things that the center first. I met Mohammed in Washington, D.C. in January, where there was a PI meeting for the new funding we got from NSF on CyberCorps Scholarship for Service program. And they have a program there, that was the reason why he was there, that has gone several cycles, and it's a renewed one. And so he leads that effort as well. And that's where the connection came. And I asked him at that time to have things. And since then, have had exchanged a few emails, and he generously agreed to speak to us today on this important topic. And so we know how the things would work. If you have questions, you can put them in the chat as the presentation goes. But otherwise, Dr. Ismail would leave about 10 minutes towards the end for addressing questions from you, and that will be the best time to have your questions addressed. So I would like to welcome Dr. Ismail. The floor is yours. Go ahead, and thanks again for speaking today.
Thank you, Dr. Asif. Yeah, so hello everyone. As Dr. Asif mentioned, I'm Mohammed Ismail. I'm the director of CEROC at Tennessee Tech University. And the talk I'm giving today is on emerging technologies for cyber-physical power system security. So this is an outline of my talk. I'll tell you a little bit about Tennessee Tech and CEROC and what we do. Then I will take, let's say, 5 minutes to talk about cyber-physical systems. And after that, we will focus on power system as an example of cyber-physical critical infrastructure. And we'll talk about how to secure this system with some emerging technologies. One of them is the AI-assisted cyber security, like to develop intrusion detection systems with AI. And then the other one is to use quantum technology to defend these systems and infrastructure. So we will begin with a little introduction of Tennessee Tech and CEROC. So Tennessee Tech is located in Cookeville. So the city of Cookeville, it has a very nice location in the state of Tennessee, almost 1 hour and 30 minutes from 3 major cities like Nashville and Knoxville and Chattanooga. So it has a very, I'd say, strategic locations from these 3 major cities. And we are also roughly 1 hour, 15 minutes or so from Oak Ridge National Lab, where we have lots of collaboration with them. The largest college in Tennessee Tech is the College of Engineering, and the largest department is the Department of Computer Science, which is the home to the cybersecurity concentration. Now, the Cybersecurity Education, Research and Outreach Center, that's CEROC. This is a college center, so it's a center in the College of Engineering. It was virtually established in October 2015, and actually this year we will celebrate 10 years of the establishment of CEROC. And then it was physically established in January 2016, and today we are located in the new engineering building in Tennessee Tech. That's Ashraf Islam Engineering Building. We are, as Dr. Asif mentioned, we are the home of the SFS CyberCorps Scholarship for Service program. This is an NSF funded program. We had 58 scholar since the program started here at Tennessee Tech in 2016. And according to the NSF, we are ranked among the top 10 in the nation in terms of size of enrollment. And we are also the home of the NS3. This is an online seminar series that aims to serve as an onboarding program for new SFS scholars from across the nation. We are also participants of the DoD cyber scholarship from the Department of Defense. Now it's called Cyber Service Academy, and we have been participants in this program since 2018. And we also host the longest running Gen Cyber Camp in the state of Tennessee, and we are home to the Golden Eagle Cyber Certificate, which is a dual enrollment program in cybersecurity. And in the new building, we have the undergrad labs, grad lab, cyber innovation lab, where we host lots of our test beds, and the cyber training room. Now, the focus areas of CIROC, number one, in education, we support formal education. Like, for example, we support through lab and technical assistance in many courses like IT security, cryptography, and some new courses focusing on emerging technologies in cybersecurity, like quantum technology, which I'm teaching this semester, spring 2025, and AI-assisted cybersecurity. We also support informal education through supporting the clubs like the Cyber Eagle Club and the Women in Cybersecurity, and lots of competition groups like the Offense and Defense groups, and we participate in several competitions over the year. In research, we focus on, I can say, 3 general clusters of topics. One of them is AI-assisted cyber physical security that leverage lots of our test beds here at Tennessee Tech. For example, our power system test bed, if we're doing power system research, our drone test bed for drone swarm research, and also our research in smart manufacturing. We also have research in quantum-enabled security, and I will talk about that a little bit towards the second half of my presentation, talking about entanglement distribution, quantum key distribution, quantum identity authentication, and so on. And recently, we started to do some research in satellite and space security. In the outreach domain, CIROC supports like Tennessee Gen Cyber on Wheels, the dual enrollment program, as I said, and we hold discovery days like for traditional cybersecurity, for quantum-enabled security, and for AI-assisted security. So that's all about Tennessee Tech and CIROC. And now I'll talk a little bit about cyber physical systems, because that's the, I'd say, main highlight of the talk. It's cyber physical systems. And before talking in details about cyber physical system, I'll talk a little bit about critical infrastructure, because many of our critical infrastructure are cyber physical in nature. So critical infrastructure, the nation's critical infrastructure, is defined as those that provide essential services that underpin our society, right? And this definition is from the US Department of Homeland Security. So you can find some examples here, like, for example, our dams. All these are critical infrastructure. Our IT, our information technology, this is critical infrastructure. Transportation system, energy, which can be, for example, the power system, the electric power system, nuclear energy, right? Nuclear also is another part of critical infrastructure. Our water distribution systems, our waste distribution system, all these are also critical infrastructure, right? So you can find, for example, for flood control, we have the dams. For oil and gas distribution, this is also another example of energy critical infrastructure. Our water distribution, all of these are examples of critical infrastructure. Now, one thing that these have in common, that they are cyber physical systems in nature, right? And so what does it mean to be a cyber physical system? So a cyber physical system, it integrates sensing, computation, control, and networking into a physical object, right? So if we are talking, for example, about power system, so the power infrastructure, the power system infrastructure, like, for example, the generators, the transmission system, the distribution system, this is our physical object, right? This is our infrastructure. We introduce to this physical object or infrastructure some sensing, computation, control, and networking functionalities, right? So, for example, from a sensing point of view, you can find, for example, in a power system that you start to introduce some smart meters, right? Phasor measurement units. All these meters are meant to observe, for example, the voltage, the current, the power flow, all these values, right? And this is meant to detect the events or changes in the environment, okay? So the first thing, which is the sensing, you start to introduce sensors inside your system. The second thing is computation. So you also have computation inside this system. Why? Because when you collect voltage values, current values, power values, the system will do some computation to figure out if this, for example, is a normal state, right? We are now functioning under normal state. So these power values, these current values, these voltage values, they represent a normal operation condition. Or maybe it represents an under voltage condition or over voltage condition, not necessarily because of a cyber attack, but because of the variations that we would see in the load in such a system, right? And depending on that state, if it is over volt or under volt, I need to take some action, right? To introduce more loads or to disconnect some loads, right? So I need to do some computation. So we do sensing to collect some values, and then we do some computation to figure out the current state of the system. And then we take in response some control action, right? Remember when I said I need to disconnect some loads or I need to introduce more loads and so on? This is a control action. So you introduce inside your system something called actuators, right? You see here something called actuators. These actuators will take the control action. For example, you figure out that you are in a high load condition in the power system because of the values you collected of power flows and voltages and so on. So you figure out that, oh, there is heavy load in the system. So now I need to disconnect, right? Some switches, disconnect some loads. An actuator will take care of that. The actuator will send the signal and then open, for example, a switch and disconnect the loads. And now I'm back to the normal load condition, right? So there is sensing. Based on the sensing and the collected information, we'll figure out the state of the system. And according to the state of the system, we'll take some control action. So two keywords we see here are sensors and actuators embedded inside the system, right? And then we have some networking, because in order for the sensors to send the signal to the controller and the controller to control the objects and all these things, we need some network components, right? These entities need to communicate with each other and have some networking, right? Now, one system that can help us to do all these things together, like the take care of the sensing piece and the monitoring and all these things, is called the SCADA system. So a SCADA system is simply a set of computers and networked devices and graphical user interfaces that will monitor and control industrial processes, right? Like, for example, to help you to do the monitoring that I mentioned about the sensors stuff, and the actuator to take care of the control action, right? So this is found in a SCADA system. SCADA is short for Supervisory Control and Data Acquisition System, right? And as the name suggests, it will acquire data from the system, that's with the sensors, and as such allow you to monitor or supervise or observe the system. And based on that, you will do some computation and maybe take some control actions using the actuators. So for example, if this is your physical system, which is the power system, and in this power system, you have cyber physical links connecting you to something called programmable logic controller, PLC, right? The PLC, this is the computer that, based on the collected information, the collected signals from the system, from the sensors, will figure out or compute the current state of the system and then send the control signal to the actuators in that system to control the state of the system, okay? And the PLC is also connected to the operation center. And in the operation center, there are the engineers, right? For example, power system engineers and maybe also some cyber analysts and so on, and they can see or observe the operation of the system on a human machine interface, right? HMI. So HMI is human machine interface. It's a graphical user interface that will show you the current state of the system, and maybe you can also have some alarms or alerts whenever you exceed a specific limit. You say that this is an overvolt, for example, condition, or you are below some limit, you say an undervolt condition, right? So you have some alarms showing up here. There are also some buttons. Maybe you want to send override the PLC and send a direct control signal to the system. So there are also some controls here that allow you to do this control action, right? So this is a SCADA representation, and this is your physical object, which is the power system. It has the sensors and the actuators, and with the PLC and the HMI, you can control the behavior of that system, monitor the status of the system, and so on. Okay, so we already mentioned that you have the physical structure of the system. You embed the sensors to measure some quantities such as voltage, active and reactive powers, current flows, and then you embed some actuators to control the operation of this system, like using circuit breakers, voltage regulators, and so on. Now, why this is an issue to us working in security is that because this system is cyber physical, and I just mentioned it's networked and there are networks and as such, and because of that, it's subject to cyber attacks, right? So there are growing threats to these systems, the critical infrastructure that are cyber physical, there are growing threats, right? Like for example, in December 2015, there was a cyber attack on Ukrainian regional electricity distributors, right? And because of this attack on these three power substations, within 30 minutes of each other, 250,000 customers lost their power. And you can see here I said December, right? So this is in the winter and in Ukraine, so it's freezing cold, and these people lost power, right? And they lost the power for some extended time, for a couple of hours, and utilities were forced to move to manual operation. Now they no longer can use the HMI, the human machine interface, to control the operation of this power system, right? So they had to move to manual operation, send their crew to figure out the issue and try to restore the power system, and that's why it took too long. And this was because a malware, right? It's called Black Energy 3 malware. This one exploited remote desktop access to damage the system and lock the HMI, right? So it's now they flipped some switches, so they disconnected the loads, and then they locked the human machine interface so that the engineers in the operation center can no longer control the system and restore it, right? So as you see, this is subject to cyber attacks. These systems are subject to cyber attacks. And we can actually tell lots of stories about similar attacks happening on water facilities, on nuclear reactors, on oil and gas distribution system. By the way, here in the US, the Colonial Pipeline attack, I think it happened in 2021, something like that. Even more recently, Ukraine was subject to some attacks on the power system, right? So these are subject to cyber attacks. Why do we have them? Because they give us more efficient control. We can control the system, monitor the system, observe the system, control it more efficiently, but they come with risks. They come with cyber attacks. And as such, we are looking today in this talk into how we can use emerging technologies to defend these critical cyber physical infrastructure. There are evolving threats, and as such, we need advanced defense technologies. So one thing that we'll talk about today is AI-assisted intrusion detection system. So you can actually develop an intrusion detection system and train it with AI so that it can tell if the system is currently under attack, right? And as such, you can take the proper defense mechanism. Another topic we'll also talk about is using quantum technology in order to share secret keys in this system. So we call this quantum-based key distribution or semi-quantum key distribution system. So we'll talk about these solutions and see how we can introduce these solutions in our cyber physical power system. Okay. Now we'll talk about the first topic, which is AI-assisted intrusion detection systems. So I'm assuming that you don't know about AI, so I'll just make a very brief introduction to what I'm trying to do here, and then we'll go straight to the topic. So AI assisted technology, you want to train, right, a machine to do some task. In this case, in our case, you want to train the machine to be able to identify cyber attacks, right? Whenever it look at the system current state, it will say the system is currently going under cyber attack. Now, there are different ways in order for you to train a machine to do this task, okay? One of them is called supervised learning, another one is called unsupervised learning, and the third one is called reinforcement learning. And in this talk, we will focus on supervised and unsupervised learning methods. As I said, there are two phases to develop this AI agent. The first one is called model training. This is when you train or you develop the model that will allow the machine to differentiate between cyber attack, for example, and normal operation scenario. And after you develop the model, you need to test this model before using the model in real environment, right? You need to test it to make sure that it's functioning properly. So you have two stages, model training and model testing. In supervised learning, so when I say that this is a supervised model, what I'm doing is that I am feeding different data to the model and I tell it the class of this data, right? So I'll give it, for example, power measurement value. I can give it, for example, voltage measurement value. I can give it also some cyber data, like the packet length, the IP address, the MAC address, right? So I can feed some data to this model. And then I tell the model, for this data example, this is a benign case. So whenever you see that the power values look like this, the voltage value like this, these are the IP addresses you are talking to, these are the MAC addresses you are talking to, this is normal operation. I mean, that's fine. It's not a cyber attack, right? And then I give it another example of data and say, but if you see the power value like this, the voltage like this, the current like this, the MAC addresses, the IP addresses look different like this is probably a cyber attack, right? So I'm telling the model, or I'm giving the model some examples and the answer to that example, right? Like this is data, it's benign. This is data, it's malicious, right? And so in the testing phase, what I will do, I will get the model that has been trained and have seen these previous examples, and I'll give it new data, right? Data that it hasn't seen before from the same system, new power values, new voltage values, some MAC addresses, and so on. And then I'll ask the model, is this benign or malicious, right? Is this normal operation or cyber attack? And because the model has been trained on some examples, it should be able, if this is well-trained model, it should be able to differentiate between the two classes with high accuracy, right? And low false alarms and so on. In the unsupervised case, unsupervised model, you only train your model with benign data. So you're just going to give it data that represent normal operation of the system, right? And what the model will try to pick up is the behavior or the pattern that it sees in the normal data, in the benign data. And in the testing phase, you will give it new data, and then it will see, does this new data deviate from the normal behavior? If the answer is yes, this data deviate from the normal behavior, then it will announce this to be malicious data. If it does not deviate from the normal behavior, it will say this is normal data, okay? So these are the two ways to develop these supervised models and unsupervised models and to test them. Now, we said in the previous slide, we said model, right? So supervised model or unsupervised model. So what are these models? So one example are what we call them shallow models. And this is just to differentiate them from deep model. There is nothing wrong with them. They're actually functioning well. And one example of this is called support vector machine. So you can develop something called the support vector machine and train it to be able to differentiate between cyber attacks. The other one is called deep models. And these are based, for example, on neural networks, right? And so if it is supervised or unsupervised based on neural network, you can see the following. If it is supervised, you can have something called feed-forward neural network. And feed-forward neural network, they are just some stacked layers. In each layers, you have some neurons. They will process the data, pass it to the next layer, process the data, pass it to the next layer, and so on, all the way to the output, right? And then based on some calculations, it will start to associate this data with a class. So this data represent normal class, or this data represent malicious class. Another upgraded version is called recurrent neural network. This is also a neural network, bunch of layers stacked and processing the data. But here, this type of data work very well on time series data, which is our case, right? Our case, power measurement, they change over the time. Voltage, it changes over the time, right? Packet length, it changes over the time. So our data is time series data. And recurrent neural network, they work well on time series data because they can capture the temporal correlation within the data. The relationship at time t1 and time t2 of power measurement, right? How it evolves over time, right? And it can capture this evolution over time and the relationship of the data at different time instances. So it will behave better on time series data compared to a feed-forward neural network. Another one is convolutional neural network. And again, this captures some correlation within the data to improve the detection accuracy. And then the last one is graph neural networks. So these are neural networks that work on graph data. And our case in power system is graph data because you can represent your power system as a connected graph. And on each node, you can see some power values and voltage and current and so on. Right? So in order of complexity, graph convolutional neural network are too complex, but it should do much better than the other types. Why? Because this one captures spatial and temporal correlation within the data, while this captures only, for example, temporal correlation within the data. And the first one, feed forward, it does not capture any correlation within the data. Right? So these are different supervised models. Unsupervised models are based on autoencoders like feed-forward autoencoder or the recurrent version or the graph version. But these, as I said, they are trained only on benign data. So now, in order for you to train these models and develop them and test them, you need to have data set, right? Because as I said, I'll give them examples. I'll give these models examples and tell them the class of that example, and as such, figure out the model parameters. We call it the model parameters, right? So where do I get my data from? Now, some people, what they do is that they try to find online some available data, maybe on Kaggle or GitHub or Google data set or so. But you will not find data set related to power system cybersecurity, especially if it is a cyber physical power system and we're talking about cyber attacks, because again, these are, how can I say it, sensitive data, right? It's cyber attack data. You wouldn't really find much of data like this. So what we did here at Tennessee Tech in order to get our data, we developed a test bed of cyber physical power system, and I'll walk you very quickly through that test bed because of our time. I'll walk you quickly through the test bed, how it looks like, and then we use this test bed to collect our data set. So we run the test bed under normal operation and we collect our benign data. Then we launch some cyber attacks on this test bed and we collect our malicious data, and then we develop these models and test them. The test bed, this is how it looks like. So in the physical layer, this is the physical layer. You can have your generators like this. These circles are generators. These are loads when you see the arrow downstairs. And this black one is called the power substation. And then you connect them with transmission lines. And then you have some loads. These arrows going down are your loads, right? So this is mimicking or emulating a power system, a transmission power system of 14 nodes. It's called IEEE 14 bus test system. And then this one here is our cyber layer, right? Bunch of routers exchanging and connecting all these power substations together and to a control center, this orange one, right? And we do this on our cyber range. So our test bed, this one here is based on a MATLAB Simulink model that is hosted on RTLab, which is the software of Opal RT. And this allows us to mimic actual power system and even to have some hardware components. Like for example, I can have a relay or an actual hardware switch and connect it to the rest of the grid to be simulation, right? So I can have a mix of real hardware components and some simulated components, right? And the other part, which is the cyber part, is just a bunch of Docker containers connected with Docker network, and we host this on our cyber range. And then we have a connection between the two, the cyber layer and the physical interface, the Opal RT device, and these two are connected, and now we have our cyber physical power system. Right? So this is how the system will look like. The human operator will get access to a human machine interface, and then this will communicate with the PLC with Modbus TCP and go through the cyber interface. Then you do the simulation of the power system, and this will feed the resulting data to the cyber layer through the cyber interface from the PLC to view it on the HMI, the human machine interface. Using this setup, we can collect physical data. I'll explain a little bit what we mean by physical data in a bit, and our cyber data. And we use this to develop our intrusion detection system. For sake of time, I mean, I'll quickly skim through that. So as I said, this is MATLAB Simulink, and we simulate our system for 6 months to have enough amount of data. So we do a simulation of our system under 6-month load profile. This will give you all the data or enough amount of data to train deep machine learning models. Our Docker container hosted on the cyber range, these will represent the substation local network, which will give you the human machine interface, the PLC, and some relay components. And then they will connect all these routers all together and to a control center. And then we configure the control center to be the node with the highest nodal degree. Now for the coupling between the cyber layer and the physical layer, we do this based on random positive degree correlation. So power nodes of highest degree are connected to cyber nodes of the highest degree. So this gives you the connection between the cyber layer and the physical layer and connect them together like this. And this will give you your cyber physical power system. Now, as I said, if you run the system for 6-month load profile, you can collect the normal cyber physical data. And then for malicious data, you can launch some cyber attacks on the system, again, under 6 months load profile. We emulated, for example, false data injection, where you inject false commands to trip off the circuit breakers. Backdoor, where you gain access to the human machine interface through some backdoor to switch off again a circuit breaker. Brute force attack for the password, right? You figure out the password for the HMI again through brute force and switch off the circuit breakers. Reverse shell, where you get a reverse shell connection and disable the PLC and switch off circuit breakers. Or ransomware, right? And here we emulated the ransomware by disabling the Modbus TCP connection, because now you don't have control over your HMI. The human machine interface is locked down and you can no longer control the system. So the data that we collect are cyber and physical data. Then we do some synchronization between the two because they have a different rate, and now we have synchronous cyber and physical data. And our cyber physical features, in the physical layer, we have 3-phase voltage, 3-phase current, frequency, active power, reactive power. In the cyber layer, we have our source and destination MAC addresses, source and destination IP addresses, the packet size, the protocol, the source and destination TCP ports, and UDP ports. Okay. Now, I'll show you some results for some of these models, the feed-forward neural network, the recurrent neural network, some autoencoder with attention, and the graph neural network. And I'll do this under 3 strategies. If you only use your cyber data to develop these models, And if you only use the physical data to develop these models, and if you use a fusion of cyber and physical data, and this was actually in this paper, the contribution of this paper, we were saying that all the existing research that develop intrusion detection system either use only cyber data, if they just look at the cyber features, or they use only physical data, and you will find that a lot in people working in power system from electrical and computer engineering. They only use physical data. People working only on computer science use just cyber data. But what we did is, okay, we said we will implement the system, collect the cyber and physical features, and then see if we can fuse cyber features and physical features and improve the detection performance, right? And the reason here is that this is a cyber physical system. If you're just looking to one layer, cyber or physical, you don't have the complete picture. And I'll show the performance metrics in terms of detection rate and false alarm. So this is our results for ransomware attack, false data injection attack, and we have other results. The paper is currently under review for other attacks, okay? Now, in this result, P means physical only features, C means cyber features, and CP means fusion of cyber and physical. One pattern that you can see is that whenever you do cyber physical fusion, you have a little bit of improvement ranging from, we'll see now in the next slide in the conclusion, I think 5 to 15%, something like that, right? This is one thing. So if you fuse cyber and physical features, it gives you a complete picture of the system with both layers, cyber and physical layers, and it will improve your detection accuracy, and also it will reduce your false alarm. Another observation here is the graph neural network, because also before that research, most of the people were just looking into feed-forward or recurrent. But we said because the system is graph data, we can capture spatial and temporal correlation within the data with a graph neural network and boost or improve the detection accuracy compared to every other model. Okay, so these are the conclusions. We see improvement in detection accuracy and reduction in false alarm. Both are great things if you use GNN models, graph neural network models, and you will see improvement in detection rate and reduction in false alarm if you use multimodal data, which means data collected from two domains, right? One is the cyber data and the other one is the physical data. If you collect data from two different domains, fuse them, you will improve your detection performance. Now, we have some advanced research where we looked into, in addition to the traditional attacks, I showed you some data poisoning attacks, and we try to improve the robustness of the models against these attacks, some evasion attacks, and these are attacks targeting the AI intrusion detection system. Also, while the attacks I have shown you, they are like direct cyber attacks, we have designed and implemented other cyber attacks using electric vehicles, right? So electric vehicles, you don't always charge them at home, you might charge them at public charging stations. And as such, we said, what if the public charging station is infected one? It has a malware, right? And so when you do the connection between the vehicle and the charging station, you can inject a malware, for example, and as such, you can harm the power grid. And we actually did simulation for city of Nashville and city of Cookeville here in Tennessee, and we have seen that you can actually spread the malware in the system within, let's say, 30 to 40 days. All electric vehicles, all charging stations will be infected, okay? So I don't have much of time, I have like 5 minutes, but I'll just introduce you to the topic of quantum, because now we talked about AI-assisted intrusion detection system in cyber physical power system. I'll talk you a little bit about quantum, but you can read more about this from my Google Scholar. I'll show you at the end of the presentation how you get that. So one thing about quantum is that quantum computing, it exploits the quantum mechanical properties of matters, like something called superposition, entanglement, and interference, to do calculation. So this is a different way of calculation compared to our classical computing way, right? And so to model a quantum computing circuit, for example, every computation has three elements. It has data, so what is your data, operations, how you do the operations, and your results. So in quantum circuits, your data is called the quantum bit or a qubit, right? In classical data, we have classical bits, zeros or ones, but in quantum computing, you have qubits, quantum bits. Also operations. Operations in classical computing, they use something called classical gates, right? XOR gates, AND gates, OR gates, and so on. There are some equivalent of these gates which are called quantum gates, okay? And the results, while it is just a readout operation in classical computing, this is called a measurement in quantum computing. So a very, I would say, like 2 minutes crash course on quantum systems, okay? Let's see how we do. Your data, as I said, are qubits. These qubits, they are different from the classical bits. Why? Because they can be in superposition. Superposition means while classical system can be 0 or 1, right? The bit, the classical bit, it can be 0 or 1. Quantum bits, qubits, they can be both 0 and 1 at the same time. The best way to imagine this is a coin, right? In classical system, you are flipping a coin. So it's either head or tail, right? That's a classical system. In a quantum system, imagine that this coin is rotating, right? You are spinning a coin. When you spin a coin and look at any instant of time to this spinning coin, it can be both head and tail at the same time because it's spinning, right? So it's between head and tail. That's what we call it superposition, right? And so we have something called orthonormal basis to represent this superposition. So for example, I say it's a superposition between 0 and 1, right? So this notation is called the Kitt notation. Psi here is your quantum state, and it's a superposition between 0 and 1. There is another basis that's called the Hadamard basis. And again, you say that your quantum state is a superposition between the plus state and the minus state, right? That's one key difference between classical data and quantum data. Regarding your operations, which how you do the computation in quantum systems, you do them with something called quantum gates, right? So you say that the quantum gate U is applied on your quantum state psi n, and this will result in an output psi out. So for example, you can have a quantum X gate that will do a bit flip operation. So if you are 0, you will become 1. If you are 1, you will become 0. There is another quantum gate that's called the Z gate. So in the Hadamard phase, it will also do a bit flip. And if you are in the plus state, you will go to the minus state and vice versa. And there is a very important gate that's called the Hadamard gate, right? The Hadamard gate will make you move from one basis to another. If you are in the 0 basis, you will move to the plus basis. If you are in the plus, you will move to the 0 and so on, right? And one very important thing is that this creates superposition, right? Because if you are 0, then you are just 0. But if you are plus, you are a superposition between 0 and 1, right? The results is called the measurement operation. So to read the result, you do something called projection, right? And when you do the result and you do the projection, your quantum state will collapse. It's no longer a superposition between 0 and 1. It's a probability of reading 0 or a probability of reading 1, okay? So you have your data, qubits, they go processing through some quantum gates, do the computation or the operation, and then when you are done, you read the results through measurement operation, right? That's how your quantum system would look like or work. And there is a very important thing that's called no-clone theory. So we cannot copy a qubit. So while in classical systems, you can make a copy of data, you cannot do this in quantum system, right? No quantum gate can do that. And so related to cybersecurity, there is the problem of key distribution, right? And you know that Alice and Bob, they want to share several keys for later use to encrypt the data. We said now that power system is subject to cyber attacks. And I give you one example of command injection attack where we injected a command and open a switch. If your data is encrypted, right? If you are using encrypted commands or encrypted measurement values, no external adversary can mess up with that because the data is encrypted and there is encrypted data, so you cannot mess up with that. So one thing is to use classical methods to distribute the keys. And this is under what we call it Duffy-Hellman key exchange protocol. For example, this is a classical protocol where you have some public parameters like G, P, and A, and some secret parameters kept at each, like Alice and Bob, at each entity. And because this is a very complex problem, right, which is called the factorization problem, no external adversary looking at these public parameters can figure out the secret values at Alice and Bob, or can figure out what is the secret key K that is at Alice and Bob, right? But this is called conditionally secure. It's secure under the condition that no adversary has computational power strong enough to solve a factorization problem, right? So this is called conditionally secure. But the thing is, quantum computers can actually break this cryptography, can break Duffy-Hellman key exchange. It can solve the factorization problem in a reasonable amount of time if you have a powerful enough quantum computer. It uses something called Shor's algorithm to do the factorization and can break this key, right? So quantum computers can break this key with Shor algorithm. It uses the concept of quantum Fourier transform, quantum phase estimation, period finding. And as such, while classical computer can take 300 trillion years to break an RSA encryption, quantum computers can break that in 10 seconds if it just has roughly 4,000 perfectly stable qubits. What I want you to know is that we are not there yet. We cannot design a hardware or implement, not design, implement a hardware of quantum computer that can give you stable qubits with low noise and low error with this number of 5,000 qubits or 4,000 qubits. We are not there yet. But when we are there, when we are having stable quantum states, stable qubits, and we have large number of qubits like 4,000 or more, then we can break these, like the RSA 2000, for example, 48, right? We can encrypt it in reasonable amount, decrypt it in reasonable amount of time. So it seems that this way of exchanging quantum keys is not safe, is not secure. Duffy-Hellman, we can break it with Shor algorithm and figure out the keys and as such decrypt the data. Now there is a quantum key distribution algorithm, another way to exchange the secret keys between Alice and Bob with quantum technology. So one example of this is called the BB84, right? BB is because of these two scientists that we have the initials B and B, and then 84 is the year when they come up with this algorithm. And this algorithm will only need one-way quantum channel from Alice to Bob and two-way classical channel between Alice and Bob. The quantum channel, you don't need to have any encryption on this quantum channel. It can be open to public. Anyone can see what's happening on this channel. But the good thing is that Alice and Bob will know that an eavesdropper is easing on this channel and figuring out what are the key values. And as such, they know that these keys are no longer secure and they switch to another channel, another quantum channel, for example, where the Eve is not there, and exchange again the new secret keys and start to encrypt the data with this new secret key. So the advantage here is that you can always tell that there is an eavesdropper on the channel who have listened to the key, right? The classical channel doesn't also have to be encrypted. You can just have it to be authenticated so that Alice knows that this is Bob and Bob knows that this is Alice, okay? For the sake of time, we won't be able to go through the details, but it has been shown that with a quantum circuit where you have the quantum bit and an Hadamard gate and H gate, and then Bob also have an H gate and doing a measurement, they can exchange the key securely. If there is an Eve in the middle doing a measurement, eavesdropping on the channel, they will know because the probability will no longer be 100% of the key. There will be a 50-50 chance of the key. And as such, Alice and Bob, if they reveal part of the key, they can tell that these values are different because an eavesdropper was on the channel. Okay, I won't go through the details of the quantum key distribution protocol because of the time. The only thing I would say is the current power system is not ready to support this technology, quantum key distribution or even semi-quantum key distribution with some limited capabilities, right? So in our research, what we did is we asked the question, which of these cyber nodes, right? I showed you that the power system is a cyber physical system, and so we are asking which of these cyber nodes need to be upgraded to be a full quantum nodes, and which of the links, because these links, by the way, are classical links in the current power system, but you can upgrade some of these links to be fiber optics and they can carry quantum states, right? Quantum bits. So which of the links need to be upgraded and which of the nodes need to be upgraded so they can support quantum key distribution. We try to minimize the number of nodes that we upgrade and minimize the number of links that we upgrade because we don't want a high cost, right? We want this to be a low cost process, right? And so we can solve this as an optimization problem and solve it with genetic algorithm because it's an NP hard problem. And when we do that, we find that our upgrade, it just uses upgrade in a 14 node. You only need to upgrade 2 nodes, right? So 2 nodes need to be full quantum nodes, the one in red, and all these node links in red need to be quantum links, and the rest can remain classical, right? If you do that, you can actually support for example, a key rate exchange of 256 bit per unit time, right? And so we achieve a reduction in the number of required node upgrade if you do this in an optimal way. Now, we have other research in our group about quantum identity authentication, quantum entanglement distribution, some quantum machine learning topics, and all of these are aimed to boost and improve cybersecurity, right? So briefly, this is what we discussed today. I told you about Tennessee Tech and CIROC. I introduced you what's a cyber physical system and how you can develop a test bed of a cyber physical power system with cyber layer and physical layer, and then how we can leverage this system to generate the data set that we need to develop AI-assisted cyber defense mechanisms. The key takeaway from here is that if you fuse cyber and physical data, you can improve your detection performance, right? And then we said, okay, also quantum-enabled technology can be very useful, like for example, in the context of quantum key distribution, for example, but your system, the existing classical system, are not ready to take this technology, right? So you need to make an upgrade of the existing components to be able to support this technology. And the problem I showed you is how to upgrade the minimum number of components in the system so you still can support this technology with a low cost, right? So as I said, we didn't get the time to talk into lots of details, but if you go to my Google Scholar, just type Mohammed Ismail Google Scholar, you will find my publication list. You'll find the papers under AI assisted security, under quantum enabled technology, and I'm very happy to receive any questions and answer any questions that you have. Okay, thank you.
Dr. Thank you very much.
Thank you.
Thank you very much for a very interesting talk. I think this you did a good job covering a lot of ground, and it's okay that we don't have a whole lot of time left. But let me see if there is anybody who has got question, and you can quickly type or you can unmute yourself and ask. It should be perfectly fine. While people think of a question, let me ask you a very quick question on
Sure.
The quantum encryption type. So I know we haven't gotten there yet, like the kind of actual computers that are, quantum and do what you are highlighting on, but that doesn't prevent us from working on algorithms, which is what you're doing, right? And so is this true that you can actually benefit, even if you are working on classical computers, on things that you would work by designing around quantum? So can you comment very quickly on the actual benefit of thinking in terms of quantum and being ready for post-quantum security, even in the absence of actual quantums being available to us?
Absolutely, absolutely. That's a very good question, right? Because that's forward thinking, right? Thinking about what will happen in the future, right? So there are a couple of things. Number one, quantum computers. There are now quantum computers, and you can access them from, for example, IBM Quantum. You can access through the cloud, IBM Quantum devices, and you have, by the way, free access to 127 qubits, and this is for free for 10 minutes every month, right? So every month you have 10 minutes to access 127 quantum computer that are there. The quantum computers that are currently available are called NISQ, right? So it's noisy because the qubits are noisy, and they are intermediate scale because the number of qubits are not too big, right? You have just a couple of hundreds, maybe maximum 1,000 qubit per system, right? And as such, they cannot solve for example, the factorization problem that I shared with you. But this, by the way, was not there, let's say 4 or 5 years ago, right? So you can see how the technology is advancing. I mean, we didn't have access to these devices, but right now you see them. And a couple of days ago, if you are following the news, Microsoft announced that they created their topological qubits, right? And now they have 5 qubits, and over the next couple of decades, they will have their like thousands or millions even of qubits on a chip. So we are getting there, right? And a couple of decades, you can see functional quantum computers. There are a couple of things. Number one, rather than waiting until the disaster happens, maybe we can improve our system now, their design, and so on. So, for example, you will find a branch of research talking about post-quantum cryptography. They are still using classical techniques, but they try to make it harder for the current quantum computers to tackle. But in my opinion, that's for the current quantum computers. So again, it will not solve the long-term problem when we have the quantum computer. Another thing is the forward thinking that we are trying to do is, okay, so what does it take to secure our systems against those? What is the minimum upgrade that we need to do? How we can use quantum rather than breaking encryption and so on, but to improve our authentication, our security, our AI models, for example, for computation. So if you ask me, I'm very optimistic. It's a matter of time when we see these systems and devices. Yeah.
Right. Thank you.
Sure.
There's a quick question Noah has, who is asking, from my understanding, the superposition of a qubit can have a near infinite amount of combinations. That's more of a question. Is that maybe he's asking for a confirmation of that?
Yes, this is correct. You can have any combination. So there is one thing that needs to be satisfied under every I'd say combination that you have. So if I go back quickly to this slide talking about alpha and beta, let me just maybe I'll do. Yeah, so the main condition is that the magnitude of alpha square plus the magnitude of beta square need to be equal to 1, right? So if you find any combination such that magnitude of alpha square plus magnitude of beta square equal to 1, then you're good. Why is that? It's because the magnitude of alpha square is the probability of measuring 0, and the magnitude of beta square is the probability of measuring 1, and at the end of the day, you can only measure 0 or 1, right? So they need to add up their probabilities to 1. Any state that satisfies this is a valid quantum state. And the answer to your question is yes. We actually visualize this as something called Bloch sphere, and there is a vector with radius 1 rotating along that sphere. So any position along that sphere is a valid quantum state, right? As long as the radius is 1.
Mhm.
Yes.
Perfect. We have run out of time, so we probably have to stop it here. Thank you so very much again for a very exciting talk. We will make the slides available on our website. So if you don't mind sharing, we will maybe follow up with an email and make also the recording available. Thank you for attending. Those of you who are Cyzer students would know that you'll have to complete a survey to make sure that we are aware of your presence here and get your feedback. It has been posted like about 5 minutes ago, so take a few minutes to complete